Welcome back, Math 170. We're going to build on 4.2 and finally introduce the integral. So we'll start off with the definition right away. We're going to talk about the definite integral of a continuous function f over the closed interval ab is defined by the notation the integral of f of x with respect to x on ab equals the limit as n approaches infinity of the summation of the f of x of i's times delta x. And if you remember just a little bit, that should look pretty familiar. If you guys recall, I'll throw this on the side for you, that we had our delta x is defined as the distance between the interval divided by n, and our x of I is defined by the first endpoint plus I times delta x. So we did a lot of that in 4.1, and we will kind of bring this in. And for the most part, you have seen this before. If you were to look at maybe the author's notation, I'll just give you a slight note. The author is using the f of x of I. So if you're kind of looking at the book, it's not that big of a deal in our sense if we understand what we're looking at, but the author uses the f of x of I star notation. But when we approach it, it's still going to be the same type of steps that will apply. So let me see, if I'm looking at the new notation, we do see the integral sign. And because it's defined as this, I kind of thought it was interesting when my previous math teacher from a long time ago pointed it out, that it does have to do with a summation. And then the integral symbol sort of looks like an S. It's a very long, stretchy S. So I thought that was kind of interesting how they made this connection. Also, a lot of times when you refer to A and you refer to B, we call these the upper and lower limits of integration. So I'd like to kind of notate that for you. So A is the lower limit of integration. Makes sense, it's the far most left point that we're dealing with. And B is the upper limit of integration. And that is the rightmost endpoint. And if we're looking at this notation, there is an importance of just making sure that your variable used in your integral function matches with what you're taking the integral with respect to. Very much so, kind of like what we were doing with derivatives. So just kind of make sure, in this class, it'll be obvious to us, but we want to make sure that these variables always agree. So if you were to see something like the f of r, we'd have to have with respect to r. Or if you see something like s of t, it'd have to be with respect to t. So just make sure the variables always agree. It won't be too rough in this class, but when we get to Calc 3, it's going to really matter. So just kind of get in the habit. Couple notes before we get started with some of the examples. If in fact the definite integral exists, it is always going to be a real number. It probably doesn't feel so profound at this moment, but we end up approaching it a little bit later in Calc 2 as well. And then this is the one that's kind of more profound for me. They are trying to tell us that if f of x is greater than 0, greater than or equal to 0, and a lot of times what I like to kind of help myself out with understanding this, if your y values are greater than 0, that means your function, or they're trying to demonstrate, your function would be above the x-axis. or sometimes it's at the x-axis with the equal to. So if this is the case, your function's above the x-axis for all x in the interval, then the integral of a to b of f of x with respect to x actually represents the area under the curve A. And we kind of dealt with this in 4.1 when we were using these limit calculations. We were calculating the area under the curve based on this. But what has to matter for us is that the areas are always positive. I'm sure you know that already. So just kind of a little caution. Area is never a negative. We knew that already. But a lot of times when they relate the integral to area under the curve, we get a little confused. Integral, it's possible that the integral from a to b of f of x dx, it's possible that it might be negative. So I'll understand may be negative. And the reason is because the function could end up being below the x-axis, and that's where the negative could come from. But if every part is greater than or equal to 0, then we have an area under the curve. So I kind of like to go over a little bit of notation and some confusion back and forth so that we can kind of compare for ourselves. We start to see integral notation, then we use the word area. So I'm going to start off with a picture just so that we can analyze this a little bit nicer for ourselves. So let's start off. I'm going to mark a nice function for ourselves. We'll count to about 6 on the x-axis. So 1, 2, 3, 4, 5, 6. And then maybe we'll count to 5 on the y-axis either way. 1, 2, 3, 4, 5. And I'll go below as well. 1, 2, 3, 4, 5. And I'll draw sort of a line segment, we'll say. We're going to be at 5, and then we'll go through around x equals 3. 1, 2, 3. And then we'll stop at x equals 6 in a way. So I'll try to do my best to approach that. And so if I have a straight edge for myself, I guess you don't need a straight edge for a sketch, but I love making it pretty. So I'll connect my dots for the most part. So I have my line segment. And what I want to look at, we're going to call this line segment our function f. Kind of keeping in mind, let's see, it ends at 6, we'll say, from there. Okay, so now, if I look at what part A is asking, it is asking for the integral of f of x with respect to x from 0 to 3. So this is where we kind of break this back into note 2. You'll notice if you go from 0 to 3, and maybe I'll mark it for us to make sure. As we go from x equals 0 to 3, our corresponding function happens to be above the x-axis. So I'll kind of highlight that. And so because of this, the integral can represent the area under this curve, which I've just colored in green. And so you kind of notice that that curved part makes a triangle. So we know the area of a triangle is 1/2 base times height. And so all we have to do is count a little bit. So got the 1/2 going on. Our base in this case, if we go from 0, x equals 0 to 3, that's 3 units. And our height would be 5. So the integral itself, because the function was above the x-axis, we could use area to represent the value of the integral. And so if we do the math on this, what do we get? 15 halves are about 7.5. Actually equal to 7.5 either way. So you notice it's just a number. Now, If we refer to part B, it's kind of the same idea. I'm still looking at the green region. If we refer to this as area, now we would represent this with using units. So if we have area, notice that area is always positive no matter what. So we should have 15 halves or 7.5. This is where the units come in, square units. So notice with integrals, we don't have to write units, but if we are referring directly to area, then we do. So let's do this again. Let's look at the area bounded by f. So f, that's our function. And the x-axis on the interval 3, 6. So that would be this region right here. And if we are looking at this a little more carefully, I'll highlight this in purple. Again, we refer to area. So we have this region and you're noticing, okay, it's a triangle. And the triangle itself, what do we have? Area equals 1/2 of base times height. Well, it doesn't matter that the function is below the x-axis. We are strictly looking at this in terms of area. So we still do the same idea. Well, what is the base of our triangle? Still 3. The height of our triangle, even though it's kind of upside down, it still happens to be 5. Doesn't matter how you orientate it. And so again, we still get 15 halves or 7.5 square units. Using units because they are directly referring to area. Now, just kind of piecing this together, we are looking at the area bounded by f and the x-axis on the interval 0 to 6. So if you notice, if we're looking at that, that would be looking at both of the triangles because we're dealing with the integral from 0 to 6. So again, I want to kind of make sure that you see that we're looking at area. So it is true, the area would equal the sum of the areas of the two separate triangles. So you can see the triangle above the x-axis from 0 to 3. That will be 7.5 square units. And then if you add that to the same area of the triangle below, that's the purple one we've shaded in, it's still 7.5. So in the end, what are we, 7.5 plus 7.5, we should get 15. But because we're speaking about area, we are still attaching the idea of units. So square units. So remember, area is always positive, and integral can be represented by area, but it depends on terms of whether you're going to get a negative or positive area. It would be depending on whether your function itself is above the x-axis or not. So maybe one last idea just to help you. Now we're going to refer to this picture and we're looking at this in terms of integrals. So if we're looking at the integral of the function with respect to x from x equals 0 to x equals 6, those are the limits of integration. A lot of times what we might do, and you'll see this later with some of the properties, is we like to break it up into nice pieces so that we can fully identify this. So I kind of see a clear cut right around x equals 3. So I'll break up the limits of integration from 0 to 3. Let's see if we can color code that a little bit. Well, I tried. We'll go again. So I'm still looking at the function itself with respect to x. But now I'll also look at the limits of integration where I can start up again at 3 to 6, and we're still looking at the function, but we're looking at a different piece of the function. So now I need to be cautious because this area that we see from 0 to 3, f of x f of x here from 0 to 3 is above the x-axis, not the entire one. So I'll look at this. F of x is above x-axis from 0 to 3. So when you want to represent it, yes, it's still dealing with the area, and we still found that in part A. So that's fine. We can call that 7.5 or 15 halves, whatever you'd like. But if you want to look at the integral from 3 to 6, if you want to point this out, this f of x right here is below the x-axis on the interval, excuse me, 3, 6. So you could still kind of look at it as area, but because it's below the x-axis, all the y values are negative. So you can look at the area as 7.5, but it should have a negative attached to it in this sense. So you can kind of look at this a little more carefully, and you're like, oh, well, if I add negative 7.5 and 7.5, I get 0 for the integral. So if we're kind of really trying to understand what integrals do, just kind of one last caution, what I'm kind of looking at right here, a little bit of a note for ourselves. When we look at this integral of f of x from 3 to 6 with respect to x, it should be negative 7.5. And it's really tempting to say that it's 7.5, but because it's below the x-axis, we have to be careful. And so what I like to think about the integral, instead of, it is related to area in a sense, but just kind of think about it as like a trash collector, where integrals will collect areas above the x-axis, and then it will dump out area that it finds below the x-axis. So this is where we kind of use the terms positive area, i.e. negative area. So I would consider the purple area of this triangle to be kind of negative space. So this is where it would dump out this part. And then the green area would be positive space. So just kind of look into that a little bit more. We'll have some time to really identify it when we analyze some of the pictures. But I'll kind of play with a few more things to kind of help you out. So integrals, they are related to area, but we just have to be careful whether or not our function is above or below the x-axis. That will kind of sum that up for you. So let's kind of look at maybe a little bit of a review in terms of a conic section to help us analyze as well. If I were to try to sketch x squared plus y squared equals 9, I do recognize that it's a circle. From the formula, both of the items are squared. The center of this circle, I don't see any shifting, so it's the origin. And then the radius always has to do with the constant that's on the other side. X squared plus y squared equals r squared, so the radius should be 3. So what I would kind of like to do is look at it in terms of, let's just draw this. So if I have a circle and the center is 0, 0, there's kind of my point right there. So if I count outwards 3 units, I have the edge in my circle, or one of the endpoints. I'll count outwards 3 units in all directions to get me guide points. So I have 4 guide points to make my circle, and I'll do my best to draw as nice of a circle as I can freehanding. Probably could have done a little bit better, but I'm sure if you practice, you have a better idea. So we have ourselves a conic section. And also, sometimes if you were trying to type this in on your TI just so that you can see it, if you were to solve for y, sometimes that helps us see. we would have y squared equals 9 minus x squared. If you take the square root of both sides, keep this in mind. I'll do this in red just to make sure. The square root of y squared, I know we've been kind of laxed on this, but whenever you take the square root of a square, you actually have the absolute value of y. And so we can look at this as 9 minus x squared with the square root. And then we kind of remember that when you do have absolute value of y, it gives you two cases. So if you were to isolate your y actually without needing an absolute value, you break it up into a piecewise function. And you have the positive case. Whoops, excuse me. There we go, 9 minus x squared. And then you also have the negative case, which is kind of explaining why we have the plus or minus in the first place. And so if we're really trying to understand this, our 9 minus x squared with the positive case would be considered the top half of the circle. And you could kind of see this put into play when you graph it in your TI. And then the negative square root of 9 minus x squared, that would be the bottom half. I know we've played with these before, but nice review to help us out. I'll use this opportunity to make the circle a little prettier if I can. So if you're kind of trying to generalize this, just so that we are clear, if you were looking at this in terms of x squared plus y squared equals r squared, that's our full circle. Okay, versus if we had the positive case, y equals square root of, let's see if we're solving that, that would be r squared minus x squared. That should just give us the top half of the circle because we have a positive case. And if you want to also just compare one last thing, y equals the opposite, r squared minus x squared. Well, that reflects it about the x-axis, so that's where we're getting our bottom half. So it's a nice general idea. So now if we kind of look at trying to understand when we insert actual functions in the integral notation, it's really useful if you recognize what type of equation you might have, because then you can deal with relating it to a shape, possibly. I know we did a lot of work with triangles in section 4.1 and even the example 1. But there are other geometric shapes that sometimes come into play. So example 2 is actually asking us to use geometry. There's where the analytic geometry comes back, so that we can evaluate the following. So if we kind of recognize what the function is, I notice I'm seeing this pattern right here. We've got ourselves the top half of a circle. Because we have a positive version. So if you wouldn't mind, you can draw a quick little sketch and kind of understand according to the format of how we compare this to our generic form, the number that comes first before the x squared, that's giving us what the radius will be, or the relation to the radius. So if r squared is 16, then the radius itself, radius would be 4. So you can kind of say, okay, if I'm centered at 0, 0, I count 4 units outwards. And up. So if it's the top half of the circle, I have my guide points, and I'm seeing that we are looking at integral as area of a circle because this is above the x-axis. So let's kind of look at this a little more carefully. They are not asking us for the entire circle. They're asking us from x equals 0 to x equals 4. So if you're kind of looking at it, you're only looking at a portion of the circle. So we can color this in just so that we can get an idea that it's a half of a circle. So just to kind of summarize, just to make sure, the value of our integral, it's for sure going to be positive because the region you are referring to is above the x-axis. And if we were going back to our trash truck analogy, we would be collecting area. So then we just have to kind of come up with the geometric shape. Well, our integral, it has to do with the circle, and I know circles have areas of pi times r squared, but it's a quarter of the circle, half of a half. So we can use the formula to help us out. And again, our r was 4. And 1/4 pi times 4 squared, 1/4 of 16 ends up being 4. And we just have pi. You can, if you'd like to approximate pi, but there's no need to. We like exact values. So notice, because we were dealing with integral, we used area to help us because the function was above the x-axis, but we don't need units on this because we are specifically looking for the number that's applying to this integral. Now, similarly, if we play with this, I want to point out that because you do see a negative portion right here, that's going to remind us that that is going to be dealing with the bottom half of a circle. And if, again, we're looking at kind of the patterns, the number that comes first is dealing with how to find the radius. So in our case, radius will be 2. And so if we can do a quick sketch with the geometry, the circle luckily is still centered on 0, 0, saves us a little trouble. And that would mean we're counting 2 units outwards. But if we're just dealing with the bottom half, we just have our guide points to the left and to the right of the center, but then we have our guide point below. So we're going to have our bottom half of the circle. And if we're dealing with this, you're noticing right away, well, if there's a negative sign in the integral, you are going to have a negative value. Now, let's look at what we're trying to apply to. X equals -2 to x equals +2. So that's the entire region that will be devoted to the semicircle or half circle. So we have a red shaded area. So the value of the integral is going to be negative for sure. See if I can write that in. Mainly because it's below the x-axis. So we are, what do we call it? We're dumping area. If we're using the trash truck analogy. But how you find the area itself is you still relate it back to the geometric figure. So area of a circle is pi r squared, but we have to deal with the fact that it's a half of a circle. So that's where the half comes in. And so we just have to understand that r in our case was 2. So 1/2 of 4 gives us 2 pi, but don't forget it's negative in terms of the fact that we are dealing with the integral. We're dumping the area out. Now, just to kind of be careful, a little note that could help you, kind of depends on how they're asking the question. So integrals, we've kind of decided they can be positive, negative, or 0, of course. But if the problem if it asked for the area bounded by the curve and the x-axis, the answer would be positive because check it out, they're talking about, where is it? Area. They didn't relate it to an integral. They just asked for what is the area. So we would just be ignoring the coordinate system, but only using it to help us understand who R is and who the center is to help us compute the formula. So if it's strictly asked for just area, the answer would be positive. Would be positive 2 pi, and we would include the units because they were specifically asking for area. And you don't really have to write the positive sign, but these two things, when they specify area has to be positive, has to have square units. So something to think about. We kind of related integrals. If you know what the picture of the function looks like from the particular upper and lower limits of x, then geometry can be used to figure it out. And also just depending, is your function above the x-axis, below the x-axis, or is it a combination of both like we kind of saw earlier? It's over here. So it's kind of nice to help you understand. And now we're going to just kind of apply a few things. Some of the things you'll probably feel are intuitive and the others maybe not so much. So I'll kind of give you the nice properties. We know we had properties of limits, we had properties of derivatives. So naturally, we'll have properties of definite integrals. And sometimes you use these when you are trying to make maybe the problem a little bit easier algebraically, or if you're viewing the geometry, it might be nicer to view one versus the other. So if I look at the difference, if I'm looking at property number 1, it's showing that you can switch the order of the limits of integration. So I'll explain this in English. So switching the order of the limits of integration will change the sign of the integral. So sometimes it's more convenient to maybe have different numbers as the starting and the ending. And you can do that as long as you change the sign of what the integral is. Now, item number 2. Here we are looking at the limits of integration. They happen to be the same. So if the limits of integration are the same, the integral should be equal to 0 because you don't really have anything to collect or dump. So you have to kind of be careful. So what are you looking at? If you just want to do a quick little picture, whatever f of x happens to be, if you're looking at the integral from a to a, well, you're not even dealing with something that could have an area. There's no length associated with your shape, whatever the function happens to be. So if the function happened to be a nice constant, you cannot find the area of a single line. There's no distance to deal with the length, or base if you want to deal with that. Now, a few of these other ones that we were dealing with, because definite integral has a definition that applies to taking limits, some of these you'll kind of think, well, they make sense because we've been using them all along. So if I could kind of pull out item number 3, this is very much like limit and derivative rules. You'll notice that if you have a constant multiplied by your function inside the integral, you can factor it out, make your life easier, and pull it outside. So it's very much like limit and derivative rules. So for instance, if I were to give you, and we'll be able to calculate these maybe in the next section, but let's just say you knew that the integral from a to b of x squared with respect to x was 1/3. Well, what would happen that if you had the integral of a to b of 4x squared dx, your property would say, hey, no problem. All we have to do is pull out the constant, kind of like what we did with the integral. I should say derivative, because we are dealing with the integral right now. And then you would just take the integral like you know and love, but we already know that this is we already know it's 1/3. So we end up having 4/3 as the answer. So factoring out a constant, kind of like what you already feel comfortable with. Now, if we're looking at this, what do we have? An integral of a constant function, item number 4. If I can do this, this is kind of like, if I can look at the geometry behind this, just so that we understand this. This is the integral of a constant function, integral. Remember, constant functions, y equals a number. With the geometry behind this, if you want to draw it really quick, if we're looking at from A to B, so snapshot of the x-axis somewhere. And a constant function usually is y equals c, nice horizontal line. So again, if you're looking at your limits of integration, well, only deal with from A to B. What do we end up having? Nice little rectangle here. So if you kind of relate this back, the height of your rectangle, let me talk about area. Remember, area base times height, length times width. Well, our height is c, and our base is the yellow portion from A to B, where how you talk about the distance is b minus a. So the area is b minus a times c, or they like to put the monomial in front, look at c times b minus a. And later on, when we deal with fundamental theorem of calculus in the next section, it'll be clear in terms of that's where the formula is being used. But right now, geometrically, we can apply it. So also, just like limit and derivative rules, the integral of a sum is equal to the sum of the separate integrals. And very much like geometry, the way I like to see it, if we are relating this to area, remember when we had some odd shapes that we had, if we were trying to find the area of them, a lot of times you could break them up into 2 recognizable pieces. And you would think, okay, well, this is the area of the first one and the area of the second one. The total area would be the sum of the 2 separate areas. So same idea. And works the same way for differences. If you have the integral of a difference, you can take the difference of the separate integrals. So you can kind of play with what works best for you. And that kind of works with area as well. Like sometimes it's easier for us to find the area of the big part. So we find the area of the big part, but we subtract off the empty space. That's if we're relating this. Now, the only thing I have to caution you, derivatives and integrals somewhat have a relationship with whenever you had a product of two functions on the inside, or you had a quotient of two functions. Remember how they had their rules? Well, you can't just split them up like you did with limits. They have issues. So we are not allowed to say that the integral of a product is the product of the separate integrals and as well the quotient. They have their own special rules. So it's kind of like derivatives. And we'll perhaps be able to explore this in calculus too. You'll kind of see what happens when you have the integral of the product of two functions. Quotient's kind of the same because product, quotient, what is the dividing is the same as multiplying by the reciprocal. So we'll have some techniques that we use when we get to that. So last property that we'll be dealing with, this is what I like to call the scenic route. And it's kind of like what we were doing here. Geometrically, when we were dealing with example 1E, we, instead of going straight from 0 to 6, we went from 0 to 3, stopped at 3, and took a break and went from 3 to 6. So we call this the scenic route. Usually involves a rest stop in a sense. But what's interesting is that the C does not necessarily have to be between the A and the B. So I'll give you a little note just in case. It might come into play a little bit later. The C does not have to be between your A and B. I mean, most of the time it is, but it's not necessary for this property. So that might be kind of interesting if we have to reapproach that later. So once we learn properties, that's great. It gives us a little more power in terms of now, if we were to try to find areas of more complicated shapes, as we have in graph 1, 2, and 3, you might be able to utilize these properties to help us figure out what areas are. So I'm going to give you a kind of a series of ideas and examples just so that we can identify them. And I always like to mark things on the graph just in case so that we can go through that. So we're going to apply, I'll switch back, but I'm going to kind of play with using, for example, 3, I'll make some up for you. I'm going to have us first refer to graph 1 to find the following. So let me give you something like the integral, let me see, like 1 to 2 of f of x with respect to x. And so let's look at this a little more clearly. Let me go back to graph 1. Looking at the limits of the integration, x equals 1, x equals 2. So let's look at that, graph 1. Okay, so if x equals 1 to 2, if I mark that, it looks the way that they're dealing with the x-axis. If x is 1 here, and then it's 2 here, we're looking at the function based on what's happening above and below. So you might be able to visualize this quite nicely. We can use shapes to help us understand. It's kind of similar to what we did earlier, but we do have ourselves a triangle. But we probably would take the scenic route so that we can use these properties. So if you want to look at this, what do you think is between 1 and 2? Well, it looks like exactly halfway. That's about what, 1.5. So we'll have our scenic route, our C happens to be in between. And we're going to add that to the area under the x-axis. And you're kind of guessing already. Well, it looks like the triangles, one has positive area, one has quote negative area, because we're collecting and then we're dumping. And you're right, but let me kind of show you just in case to make sure. If we have our two triangles, just so that you guys can see, triangles are known for having area, what, 1/2 base times height. So just to kind of get you an idea. The base of our triangle should be 1/2 because it's halfway in between. That's right there. And our height is 1. So that's going to give you the area of the triangle. It's 1/2 times 0.5 times 1. And you can find that if you'd like. And then similarly, because we're looking at the purple part, it does look like it does have the same area. 1/2 base times height. What is that? 1/2. Also, doesn't matter which way it's orientated. Base is 0.5, height is 1. Now we can find the answer, no problem. Half of a half was 1/4, 1/4. But if we're going to apply this with properties, let's kind of write it out. We're taking the scenic route. We're going to take the integral from 1 to 1.5 of our function with respect to x, and we're going to add that to our integral starting at 1.5 and stopping at 2. So taking the scenic route, and then we already realized, well, we had positive area, so it's like 1/2 times 0.5 times 1. And yes, we can relate this integral to area, 1/2 times 0.5 times 1, but because we're below the x-axis, that's where the negative sign comes in. And they both happen to have negative area in terms of, well, one's neutral, 0 would be our answer. And you can actually see that with the picture. If those areas are the same, one's above and one's below, right in the middle, they neutralize each other out. So kind of like an application of what we did earlier, but just kind of giving you an idea. Let's do this. Let's look at everything from 0 to 10. We'll try that. So this time, I'm going to look at the entire figure as a whole. So starting at x equals 0 and stopping at x equals 10. And so this would be the case of us playing with maybe breaking up these oddly shapes into nice recognizable shapes. So let me kind of designate that just so that you can see if I want to look at the entire x-axis. If I go from 0 to 10, x equals 0 to x equals 10 of my entire function, this seems like we're gonna break it up into a bunch of different areas. So I might refer, see if I can maybe color code these a little bit more, if you're interested. I already have the idea of what's happening from 1 to 2, so I could kind of demonstrate this from you. Let's look at the area from 0 to 1. I'll use orange to help you. And you're saying, okay, well, the area from 0 to 1, that looks exactly like a square, and you're right. But let me kind of use notation to help you out. So the first area, I'm going to look from 0 to 1. It's my f of x. And that area happens to be a square. So I can call that, I'll look at area 1, if you guys would like. I know it's a lot of switching back and forth, but that helps us. And what's the area of a square? Side times side. And if you look at it carefully, I know it's a lot of flipping back and forth. Side is 1 unit, the other side's 1 unit. 1 times 1 is 1 unit. So that's where I'm getting the 1 from. Now, I also want to look at kind of like what we were doing earlier. Let's break it up from 1 to 2. Well, we already know the answer to this. That's area 2. But we just did this in part A. We ended up getting 0. You guys can see, I'll mark it for you just in case. I'll call all of this area 2. The shapes that we see, one's above the x-axis, one's below, and they perfectly neutralize each other out. Now I'm just moving over and I'm going to say, okay, well, it looks like the next clear shape, to me, it seems like I can go from 2 to 3, and I do have a triangle that's below the x-axis. So if I want to look at that triangle just a little bit, I have to kind of keep in mind, I can pull it off to the side so we can see it. It looks like the base is 1 as well as the height. So if we want to play with the area of the triangle, what do we call that, A3? A3, 1/2 base times height, that's 1/2 of 1, which gives us 1. So that's area 3. Now, by the way, you kind of play around with this. I'll write this out just so that we can see this. So we're going from x equals 2 to 3. That's the lower limit, upper limit. And we realize that it's entirely below the x-axis. So our area 3, we would be subtracting it off. We'd be dumping it. So again, what was that area? It was equal to 1/2 of 1, which is just 1/2, right? So we'd be subtracting off 1/2. Now, let's keep moving and just try to figure out what I can collect and dump. The next region I am seeing looks like to me, and I'm going to assume, but I can go all the way from x equals 3 to 7. And that looks like a nice half circle. So my area, if I can kind of shade this, it's a half circle. What do we call that, area 4? It's a half circle that's completely above the x-axis. So if we kind of remember, it's a half circle, that's 1/2 times pi r squared. So we just have to understand who is our radius. And if I'm looking at this, I have to say, well, it looks like the center is over here, and the radius is most likely 2 units. So see how I'm breaking this up into shapes. So if I want to designate that, just so that we see, we switch back. And I'd be looking at what's the, oh, shame on me. I forgot to put it with respect to x. Notation's important. Okay, so let's look at this. We're going from x equals 3 until 7 with respect to x. And we realize that it was completely above the x-axis, so we're adding on that area. And that area happened to be, it's a half circle, so 1/2 times pi r squared. Just remind us what it looked like. Be a little careful here. It looks like the radius is 2 units. So that's where we have that. And I can clean it up in a second. I just want to make sure we're seeing how we're breaking this part. So let's see if we got the entire function yet. We're almost there. There's more than one way to approach this. I'm looking at now what's happening from 7 to 10. And the way I see it, I am looking at area, but everything's completely below the x-axis. So what do I call that, area 5? And I can recognize that as a trapezoid. Or if you're interested, you could try to break it up into somewhat of rectangles and triangles. but area of a trapezoid, if you remember, it's 1/2 base 1 plus base 2 times the height. So in our case, our base 1 is 3. That's the distance from 7 to 10. Our base 2, if I want to be a little more precise, I know for sure it's 1 unit, and it looks like we're going to estimate it's 1.5, 1/2. And then our height happens to be 2 units. Now, because that is directly, completely below the x-axis, it's going to be negative. So I'm going to have to write that in just to make sure. I have one more area. The integral would be from what? 7 to 10 of our function. And so technically we have the area 5, but because, I'll be a little more precise, because it's completely below the x-axis, that's where we have the subtraction. And so we had this trapezoid. It was 1/2 base 1 plus base 2 times height. I remember the height was 2. My base 1 was 3 and 1.5 was the base 2. I'll double check though. Normally we don't have to keep switching pages. The 3 plus 1.5, we're good. So now, my friends, we actually have the sum of our areas. So we could kind of simplify a little bit. Take your time. What do we have? 1 minus 1/2. We have 1/2 of 2 squared. That's 2 pi. And then let's make this prettier, subtracting off. 3 plus 1.5 is 4.5. 1/2 of 2 is 1. So we should have subtracting off 4.5. So now if we're going to combine all of our terms, we have 1 minus 1/2 minus 4.5. So it looks like we should have -4 and then plus 2 pi. That wasn't a like term with anything. So that would be the area, well, not the area, it should be the value of our integral from 0 to 10. So we split it up into a bunch of different areas. And so sometimes it takes a little bit of reading the graph a little bit. And for the purposes of these problems, I always make sure that if something looks like it's halfway in between, we can definitely assume. If something looks like a half a circle, we can assume that is a half a circle. Don't get too complicated here. Okay, let's see. So we kind of have a little practice. We can do a few more. Let's use graph 2 this time. And how about we go from, maybe I'll just go from like 0 to 7. Okay, so graph 2. And let's look at, I'll call it part C, I guess. The integral, I'll go from 7 to 0. No, I'll make it more fun for you guys. Okay, so let's look at this. Assuming all these are f of x's, we are going, it's saying the integral from 7 to 0. And when you kind of look at your graph, you're like, wait a second, seems like it's out of order. Wouldn't it be more convenient to go from 0 to 7 maybe? Wouldn't that be kind of nicer? And yes, I agree with you. So now we can kind of say, oh, we can utilize our property. And so let me see if I can mark this just so we see. I'd rather go in order, 0 to 7 instead of 7 to 0. But you can look at it backwards because it is a graph if you're interested. But our interest is understanding that if you want to switch the limits of integration to make this understandable, we should be saying, okay, if we switch, we have a negative, and we can go in order. We have f of x with respect to x. So now, what I'll probably be doing is just understanding that there is a negative outside everything I deal with. But I want to see 0 to 7. How many shapes am I able to break this up into, or is it one nice shape? Let's go back and look. So 0 to 7. I could do this in a few different ways. I prefer, I could do this. I'll play with you. I'll see what happens. You know, I would say I'd be inclined to try to use a trapezoid, but the problem is that you're not quite sure. You can kind of say, yeah, that's a trapezoid, but that doesn't look like 1/2 for sure. So I might kind of say, okay, trapezoid out of the picture. I know for sure I can look at this piece right here. That looks like a nice triangle. So, okay, I'll deal with that. And then maybe, because we are looking at graphs, it might be, maybe it's nicer to say, why don't we look at this in terms of breaking it up? We have some clear squares going on. Those are nice to count. I don't know if you guys can see this, but I already know what that area is. 1, 2, 3, 4, 5. So you can do that as well if it's clearly marked on your axis. What would leave us with an area of partially a triangle. It's above the x-axis. So maybe call this area 1. I'll call the pink part area 2. And we already know it's 5. And then I can look at, yeah, I can definitely look at the other part. Looks like a nice little triangle from here to here. I'll call that area 3. And then I have area 4. So I kind of just broke it up into 4 different areas. And I know there's more than one way to go, but kind of helps me see that, you know, I'm really happy when I see triangles because I know those. And if I see squares or rectangles, that's nice. So what we can do for ourselves, I could kind of play with maybe understanding that we are looking at everything. So let's look at area 1. So I'd be saying area 1, area 2, area 3, and area 4. Now, if I look a little closer, let's kind of analyze this a little bit more. So I have 4 different areas I'm dealing with. Okay, so for sure, area 2, that's 5. So we're good to go on that. Let's put that into play. I'll put that right in there. So that's going to be a 5 right there. I'm really interested in looking at, look at area 3 and area 4. Without doing any math computations, notice that both of them have the same base. So both of their bases are 2, and their height is 3. One is completely above the x-axis, one is completely below the x-axis. So what I might be interested in is saying, hey, do I even have to bother? Area 3 and area 4 neutralize each other. So you could say, let me make sure who's positive. Area 3, area 4, I could say, well, technically it's below the x-axis, so I'll adjust my sign. And so what they end up doing is they neutralize each other out. They're the same. Same area minus the same area, so we get a 0. Make our lives easier. Okay, now just kind of keep in mind, so technically what we're doing is what we're adding on a 0. I mean, that shouldn't make a difference, but I'm trying to justify. The only thing I have to deal with is area 1. So let me go back and say, I think area 1 was a triangle. And yes, it is. So I know triangles have 1/2 base times height. 1/2 is 1/2. In my case, the way I'm looking at my triangle, my base happens to be 2. And my height also happens to be 2. So now we can say 1/2, 2 times 2. Don't we just get a 2? And it's above the x-axis, right? So area 1 is actually a 2. Okay, so everything's above the x-axis. Let me make sure I'm carrying down what I need to carry down. Because we switched the limits of integration, we had to keep that negative sign. So at the end, what do we end up having is -7. That's the value of the integral from 7 to 0. So I know there's more than one way to do it. This is the way I saw it. Sometimes if I'm relating integrals to area, counting squares is a lot easier, but I know you could have broken it up in many different ways. It's kind of nice if you can visualize areas that are collecting and areas that are dumping. If they're the same, it saves us some time with computations, but feel free to analyze it as you go. And let's see if we can play. Let's do graph 3. Might as well give you one from there. I'd like to utilize all of them if possible. So let's look at graph 3. And if I'm looking at graph 3, let's go from, what do they call it, g of x? Let's look at the area from 1, let's do 1 to 7. So I'd be looking at what shapes are made as the x values span from 1 to 7. And so the way I'm seeing it, looking at, okay, we have ourselves a triangle, trusty triangle. So we can call that area 1. And then my friends, it looks like you have a semicircle again. Call it area 2. And it looks like we also have a teeny tiny triangle as well. Area 3. So now just paying attention that the area of the semicircle is completely below the x-axis. So I know we're going to have negative area. And then the triangles have positive area because they are above the x-axis. And actually, I want to make it more interesting for you guys. So I'm going to go from 1 to 7. Let's throw a constant in there as well. So look at g of x. And so what does that constant really do? That constant, all we're allowed to do is say, hey, let's just pull it outside. Let's not have it affect anything. It's a constant times a function. So now what that gives us is 3. And now we can kind of say, well, we did break it up into 3 different areas. So what do I have? Area 1. And I already recognize that area 2 completely below the x-axis. So we know whatever we find, we'll subtract it off. And area 3 is completely above the x-axis, so we know for sure it's positive. So now we can kind of go in and just calculate. So let me look at area 1. Off to the side, area 1. I know it's a triangle, 1/2. Base looks like it's a 1. This time height is a 2. So that area happens to be a positive 1. So area 1, good to go. Subtract off area 2. Let's look at this semicircle a little bit more in depth. So I know semicircles, pi r square, but it's a half a circle, so we have the half. And so we just have to understand who is the radius. So I'm going to look at this a little closely and say, okay, looks like the center's here. Looks like the radius is 2. So I should have, I'll go sideways, 1/2 pi times 2 squared. 1/2 of 4 gives us 2 pi. Let's put that back down where we had it, 2 pi, but it's subtracted. And then we're going to add on area 3. Let's find out what that looks like. Area 3 is a small triangle. Still a triangle, so 1/2 base times height. It looks like the base is 1 and the height is 1. So 1/2 of 1 times 1 is still 1/2. So now we can add that on. Oops, let's make this consistent. So now I just want to make sure I'm looking at just combining the like terms. So we should have what? 3, still there. 1 plus 1/2, 1.5, or 3/2. And then we saw the minus 2 pi. And then if we're being precise, you probably want to distribute the 3. So 3 times 3/2, 9/2. And then 3 times 2 pi is 6 pi. So 9/2 minus 6 pi is our evaluation of our integral. So a nice little idea with analytic geometry to kind of help you out with when your functions are clearly making some recognizable shapes based on the way they're laying on the x-axis. So some things to analyze for yourself. Feel free to play around. I know they have some of these in WebAssign as well. I'm going to leave example 4 up to you to kind of interpret. What we have is a more open function in a sense of that we're kind of looking at it as they're not clear cut shapes. But if you're kind of listing the definite integrals in ascending order, just kind of pay attention to the limits of integration. And ascending order, just remember, means what? Smallest to highest, or largest, if you want to say. So you could kind of pay attention to, depending on the limits of integration, you could kind of say, well, A to B, if I'm looking at it, just to give you an idea, it looks like it has a positive area. If you look at A to C, you could kind of say, well, it looks like it has a larger positive area, and you'd be dumping out some negative area, but not, you still have positive area in the long run. If you go from A to E, then you kind of have to interpret what that looks like. What A to E is saying, okay, we have larger positive area, we're dumping out some smaller area, but we're adding on some more area. And then B to E, you could kind of say, well, I'll have you guys play with it. You guys can interpret this, but if I'm going from B to E, it looks like I have a larger negative area than and a smaller positive area. So in the end, it ends up being negative in a way. Just got to figure out how negative. And then what do we go? C to B? Where is C to B? Oh, C to B. Just to give you an idea. I'll erase some things so that doesn't make it too messy. Notice that C and B are not in order, so this is kind of where we would utilize, let's make it understandable and go from B to C. So you can look at it that way. F of x with respect to x. If you go from B to C, now you're noticing, okay, well, B to C has negative area, but when you flip-flop it around, negative, negative will give you some sort of positive area. Whoops, I should go negative times negative just so that gets you an idea. So just some things to consider. This is a good exercise for our brain. So that's a negative area. We already have a negative number. So in the end, it's going to be a positive area in a way. Positive value of the integral. So you're going to say, like, how positive is it? Is it, is it bigger than our biggest positive value? Is it a little smaller? So interpret and then check back with me. See what works out. But it's good for our brain to kind of think about these things when we don't have clear-cut numbers. Okay, so let's bring in a little bit more. Let's kind of revisit 4.1. This might kind of incorporate some of the ideas we learned earlier and also kind of give us clear-cut numbers. So if I'm looking at the integral from 0 to 4 of x squared with respect to x, later on, like in the next section, you're going to find a nice shortcut. But we have to be careful because if they're asking us to use definition of the definite integral, we can't take that shortcut. Maybe we can use it to help us figure out what the answer should be. Like some of you might already know it already. Maybe you read ahead. But if you're asked to use the definition is us finding, remember it's the integral, the limit as n approaches infinity of the summation of I equals 1 to n of f of x of I delta x. And so that would be the integral from a to b. That is our definition. So we're going to have to revisit 4.1 and what we were doing. And pretty much the idea is, let's come up with this part first, and then we'll use limits to help us out. So remember that. We did a lot of examples on that, but let's kind of run through that. I always look at what is delta x first. And that happens to be our b minus a over n. In our case, remember that upper limit is b, lower limit is a. So that gives us 4 minus 0 over n. Nice little 4 over n. And then we kind of come up with who's our x of I. Well, our a times I delta x. Our a is 0. Delta x is 4 over n. I'll clean it up just a little bit. I'm going to go sideways. It's going to be 4i over n. And we're like, okay, kind of coming back. I practiced these a little bit. Compute your f of x of I. Well, we just plug in. Our f of x was x squared, so we're saying it's 4i over n squared. Simplify a little bit nicer with 16i squared over n squared. And then look at item 4 is just to connect these two. We're looking at f of x of I times delta x. So we're taking the 16i squared over n squared, and again multiplying it by delta x, which is 4 over n. Maybe clean that up slightly. 16 times 4, 64 I squared over, this time it's n cubed. So now, a little bit nicer, what we can do for ourselves is look at the limit as n approaches infinity of the summation, but we already know what f of x of I times delta x is. It's a lot prettier. So we should have 64 I squared over n cubed. And if you remember, what was kind of nice is that when the summation was dealing with i's, anything that was a constant or an n could have been factored out. Not completely from the limit because we have n's in the limit. But you can say, oh, okay, we can take 64 over n cubed out and then kind of deal with the summation. And what's left over in the summation is the I squared. And then if we remember that, those were some of the limit, not the limit properties, the summation properties. So that right there, kind of look back, what do we have? N times n plus 1 times 2n plus 1 all over 6. That was one of our properties from the last section. But what that allows us to do, when I look at it a little more carefully, we still have the limit as n approaches infinity. You still have to deal with the math, where we have 64 over n cubed. And so what you can do, if this is helpful, I see the 64 and the 6. If you're interested, you could reduce it out right now. You could also just pull it out and deal with it later. But let's make our lives easier. I'll pull my calculator out. My brain's already thinking too much about calculus. So what do we have? 64, reduce it out with 6. I know we could do this in our minds, but might as well be accurate. So that's what, 32 over 3. If you guys want to see that one more time, we're just kind of reducing. So we could pull that out, 32 over 3. Then deal with the limit as n approaches infinity. And if you want to take a liberty and you do the invoking of Bill Gates property at the same time, we can look at our leading terms. So our leading terms are n times 2n. So what do we have? If we look at this, I'm missing something. Oh, that n cubed, right? Don't forget, we still have this n cubed in the denominator. So if you're interested, you're saying, what is that? N squared over, wait, n times n is n cubed over n cubed. Well, the n's completely divide out. I'll make it a little prettier for you just so you see. So what I can do, save myself some time. This 2 can come out to the front. So 32 times 2 is 64 over 3. Just so that you see this, I have limit as n approaches infinity of n cubed over n cubed. Well, what do those n cubes do? They end up dividing out to be 1. And what is the limit of 1? It's 1. So your final answer for that integral is 64 over 3. Isn't that pretty? So just a little practice there. You can kind of go with the fact that, okay, I heard there's going to be a shortcut later, and yes, there is. But remember, if they specify in the directions to use the definition, you are stuck with using limits and summations. So please pay attention so that you gain all the points that you can. Let's do one more before we stop for this section. I'm looking at the integral from 2 to 4 of x cubed with respect to x. And I could play around if that's something that you're kind of looking at. We could do this directly, but I would have an issue with looking at when you're trying to calculate your delta x, and you're looking at your f of x of I and your a's, it's going to be a little interesting. So I'll let you kind of play with it if you're interested in doing this directly, but I'm interested in kind of utilizing some of my properties. And what's useful to us, what we're really interested in seeing, is a lot of times when you have 0 as one of your upper or lower limits of integration, life is a lot easier when you're calculating your delta x and your x of I. Having a 0 is very nice because then when you square and cube things, you don't have to square binomials or cube binomials. You can play with it, see what works for you. But I'm going to give you my technique and see if this works out. So I'm going to take the scenic route. And what I mean by this is I rather have zeros. It's somewhere in my limit integration. So I'm going to exchange one hard integral for 2 nicer ones. So if I can play with this, maybe I'll leave this up to you to play with, but I'll start you off nicely. Let's see if we can. Okay, so I want zeros, but if you guys notice how number lines work, if you're looking at 2 to 4, you notice how zeros somewhere over here. It's not in between 2 and 4. So what we might want to do for us is always kind of keeping the lower limit lower at the beginning, and we'll go with this later. I'm going to go from, instead of 2 to 4, I'm going to go from 2 to 0. So I'm looking at x cubed with respect to x. I'm going to go from now, my upper limit, so let me kind of let me kind of mark this. I'm still preserving the lower limit was originally in the, well, the lower limit was originally lower. I need to preserve that. And I still want to preserve, oops, I want to mark that so you guys can all see. Here we go. I still want to preserve the upper limit. So I want the fact I want to see this 4 going on. But what the scenic route allows us to do is if you're choosing your C, so to speak, that's what we're looking at, you can go outside and come back in. So we're exchanging one hard integral for 2, I'll quote, it's easy. Nothing's easy, but at least having a 0 is a lot nicer. So now, remember, the goal is to have zeros in the lower limit because it makes our x of I a lot nicer, which then makes our function evaluated at x of I a lot nicer and quicker to evaluate. So when you kind of look at this one more time, what we need to do is let's switch it one more time. I still want 0 as the lower limit. So what I'm going to do, switch out. If you have this, what's going to happen now is the limits change. It goes from now 0 to 2. And now we are cooking because now we know how to do those quite nicely with all the practice we just did here and all the practice we did in 4.1. Now, it's important, especially at this point, that if you forget to switch it, you've basically exchanged one hard integral for 2 hard integrals in this case. I know it looks tricky. 0 looks nice on the top, but at this point it's not if you're using the limit definition. So like if you're exchanging one hard integral for 2 hard integrals, that's like getting a TV for $200 or something and then saying like, hey, I'll give you $900 and not a penny more. So it doesn't make sense. Like you want the cheapest way to go or the nicest way. So I want to try to help you out with that. So now that we have that, we can now approach these problems a lot nicer. So if I can maybe help out a little bit, look at each one separately. So, okay, let's look at the integral. I'll try to separate this by color coding. The integral from 0 to 2 of x cubed dx. So we're going to come back because it's a sum of 2 integrals. So integral from 0 to 2 of x cubed dx. That's nice because we have limit definition, n approaches infinity, summation, I equals 1 to n, f of x of I times delta x. Well, before we do anything, what's our favorite thing to do is the 4 steps to help us out. What's our delta x? 2 minus 0 over n, so that's 2 over n. Let's write that in nicely. There we go. Delta x is 2 over n. Now x of I, that's 0 plus I delta x, which is what, 2i over n. That's why we care so much to switch and have 0 as a lower limit, because you don't have that extra term in the x of I. F of x of I, that's cubing your 2i over n, and that's nice too, just having one term to cube. So does that give us 8i cubed over n cubed? And then f of x of I times delta x. So what does that equal to? F of x of I is 8i cubed over n cubed, and delta x is 2i over n. So we end up getting, what is that, 16i to the 4th over n to the 4th? Or is it I cubed? Let's look at that a little more carefully. These are f of x. Yep, okay. Fun times. We'll deal with this one. So what we end up having, finally, and I'll let you kind of do the rest because I'm at this point, you want to work on it. We should end up seeing the limit of the summation I equals 1 to n. F of x of I, what do we have? 16i to the 4th over n to the 4th. A little more fun. Now you guys can play. If you're interested, you can say, I'm going to find out by taking factors out. Do I have something that helps with I to the 4th? We'll go with it. And then also, don't forget, you're going to find a number here from your first idea. And just kind of remember, it's going to be negative. And we're going to have some number that we're getting from the purple part. It's going to add on. What are we going to have to do with this part? What do you think? Same idea. So I'm going to let you play with that, see what you come up with, and then you're going to start to appreciate, oh, there's this fundamental theorem of calculus going on. I believe we should get 60 when we're done, by the way. So we're going to get a negative number plus another number, whatever it happens to be. I'm going to let you play with that because you can practice. But I'm pretty sure we're supposed to get a 60 if I'm using the fundamental theorem of calculus. Come back and check with me. Let me know. So moral of the story is utilizing the nice properties so that we have 0 as our lower limit. It's going to help us out a lot with this. But eventually you're going to do a lot of these and say like, oh, isn't there an easier way? And good news in 4.3, there is. So I'm looking forward to seeing you then.